the things that we are supposed to discuss this week. And I think in the end, we can take, I think, whatever you have asked the last week, right? On the L2 part. Okay.
Yeah, sure, no problem.
Yeah. So, yeah. So we will mostly this week is on segmentation and detection. Okay. Um, I think classification, segmentation, and detection are the typical problems in vision, right? We know segmentation has um, and detection. Let's say detection. And segmentation, we have two things: instance and semantic. Here, semantic. So here we have um, single shot detectors and two stage detectors. So difference between instance and semantic is now,
Yes,
right, given an image, um, yeah, instance, one has to detect the instances of the same object multiple times, right? Something like that. Semantic is you need to um, assign a label uh, to the, I mean, for one object, you need to assign one label. Right? That's semantic. Um, and yeah, so here we have something like YOLO detectors, and here we have something like fast, and RCMS. Faster, RCMS. Okay, so yeah, and for detection, we use, so object detection, we typically use um, as pre-trained CNNs, right? Model is pre-trained CNNs, and then based on the feature maps, we try to come up with some, say, classifiers, right? Some classifiers and losses. I mean, these losses are typically for the boxes, right? Bounding boxes. One may assign, right? Um, Losses for bounding boxes and the objects themselves, plus objects. Okay, so for segmentation, we typically take the units. So we have this image, and we it, it will we get the feature maps by applying various con layers, right? We get some big feature map, and then we keep increasing, going back to this, the segmented portion. In a way, segmentation is also sort of classification, but it's a pixel level classification if you think about it. Um, all right, so yeah, so these are the things that we will discuss today. I mean, most likely it will be a short one today. Questions are also, I think, they're easy, and yeah, we can discuss if you have any questions afterwards. I'll share the notebook. Today is how we just see the pre-trained YOLO detection algorithms, right? So yeah, here we install all the requirements. This notebook will be made available
Okay.
and run it for yourself offline. And these are installing the requirements. And here we import the YOLO model. Okay. And this is for loading the image and apply the necessary transforms. Right, the image path is given here, and we have multiple YOLO models, right? And we just see how this each of the models perform on a given image, right? So for each of this model, right, we run the inference. This is the inference function, and yeah, that's so we're just doing inference from the pre-trained YOLO models. We pick an image and we just do that. Okay, so this is how the inference with YOLO 5S model looks like, right? So it's able to detect the persons, cars, and these are the confidences with which it detects, model detects. And the same thing with 5M. Here we can see more or less the same thing, but we do have this traffic light as a detect, as a new this thing here. Okay. And yeah, the same is the performance with the model 5L and the performance with model 5X. And same thing with YOLO 7 inference probe, right? Yeah. So here we can see bounding box are sort of narrow compared to the previous version. And it's able to sort of detect truck here clearly. And
I think higher yellow versions get complicated, right? The architecture gets complicated.
yeah, that's right. Yeah. Architecture and losses they come up with are sort of involved. And yeah, this is just you can take it offline and do inference and observe what's happening. Um, yeah, this is segmentation. As I said, we will use the units typically for segmentations. Um, this is for generating the data for the segmentation thing. And yeah, so here we only generate the segmentation for toy data. These are the
Okay.
input images, black and white, and we want to do this classification, right? On this, like we need to identify. So this is you can treat plus as one class, square as one class, right, and circle as one class. Okay, and these are the ground truth mask. Uh, this is the original image. This is a mask. So now, given an image, we need to throw a mask like this after training. So that's the task.
So input
There's-
input is the black image.
Input is a black and white image, yes. And here,
Okay.
each of the object is a class. We can consider it as a class.
Okay.
Okay, now given this class, we are giving this mask. So this is something like oval, right? Oval is one class. So we need to color the pixels within this region with yellow and color the regions with the pixels with plus as some other color, right? Something like that. That's the task. It's sort of segmentation only, right? We are assigning the class to each pixel.
Okay.
And yeah, so yeah, this is just a data preparation part, the code, and this is our input image. Now we want to classify this. So now we define a unit, the one thing I just briefly described, right? And here, this is the loss. We use the cross entropy loss only for this. Yeah, we just train here and we predict. This is our this thing, our post training. This is the ground truth image, and this is the ground truth label segmentation mask, you can say, and this is our predicted mask. This is doing pretty decent job, if you
Very
can
good.
see. Right,
And it was also able to detect overlapping objects also.
right, right. But it's sort of easy in the sense, I mean, compared to natural images, it's relatively easy. It's a sort of synthetic thing. Um, yeah, you can play around with this, or maybe you should pick up some probably real data, and if you have resources to train, then you can do it. The resources means GPUs and all, right? Otherwise, it's for training deep learning is costly. It's a costly.
Very good.
Yeah, so best thing is to take any pre-trained models, download from the internet units, and then you can see assigning the doing the inference on the real world images, and maybe you can just fine tune to check. And 1 or 2 layers probably we can do it on laptops, but not the entire model itself. Yeah, and yeah, I think, but this is a decent thing to play around with. Okay, so let's go to the questions. I mean, questions today are also uh, they are, I mean, they are descriptive kind of thing, right? So, which of the following statements correctly distinguishes between object detection, classification, semantic segmentation, and instance segmentation? Right. So, yeah, classification assigns a single label to the entire image, indicating the most prominent object class, while object detection identifies and localizes. I'm reading the option B. That's true because multiple objects in an image, we're drawing bounding boxes around them. This is wrong. Object detection involves classifying each pixel in an image. A is wrong. And B is
Yeah, this
fine.
is wrong.
Semantic segmentation assigns unique label to each instance in an image. This is also not correct. And so the B in instance segmentation, the goal is to classify and differentiate each instance of an object in an image. That's true. While in semantic segment, the goal is to classify each pixel into a fixed set of categories without distinguishing between the different instances of the same class. Okay. Um, yeah. The YOLO object detection models from YOLO version 1 to version 4 have undergone significant changes in architecture, optimization, and loss functions to improve detection accuracy and speed. Which of the following statements about YOLO V1 through V4 version 1 are true? So YOLO version 1's loss function being primarily focused on regression of bounding box coordinates heavily penalizes small localization errors, but it struggles detecting small objects due to grid cell constraints and equal weighting of class and localization losses.
I haven't read the yellow paper, so I can't answer this one.
Yeah, I mean, one needs to know all these versions
Yeah,
in detail.
technical
To,
details.
yeah. So see, I mean, you can browse through these options and see. YOLO version 2 introduces the use of anchor boxes and multi-scale training strategy, which improves detection of objects at varying scales, but continues to use the same loss functions as YOLO V1, which makes it less effective in handling class imbalance and high confidence. I mean, it typically this is not the case. I mean, like version 2, when they upgrade, they do have an impact on loss functions, right? Yeah, you can. I mean, you can, even if you don't know, you can go through options and eliminate the ones that are not trivially not true. YOLO version 3 improves upon version 2 by using multi-scale feature pyramid and binary crossing for philosopher classification, which reduces the false positive rate in dense object environments. However, YOLO version 3 abandons anchor boxes in favor of direct regression approach to reduce localization. Probably this is also not true because YOLO uses anchor boxes, to my knowledge.
Okay, so all the versions of Yellow use anchor boxes.
Yes.
Okay, okay. And what is a feature pyramid? Multi-scale. I mean, so I think at different scales we extract different features. Is that so?
Yeah. And YOLO version 4 incorporates innovations such as, I don't know what it is.
Mhm.
Fish activations, mosaic data augmentation, which greatly enhances detection performance. Its loss function further refines balancing between objectness, class localization, and with the addition of CIOU loss, which improves convergence localization accuracy over previous versions. Yeah, before even you go to exam, just go through what this each of the versions have improved upon. Either from
There
the
are total, I think, 10 versions.
okay, no, whatever is being taught in the lectures, just go over those versions. I
Okay.
don't think so. They're allowed, right? I think A and D are true. Yeah, I mean, you can pretty much eliminate B and C by reading the options carefully. Um, yeah, Singular V2 doesn't use same loss function as V1. This is wrong because they don't abandon anchor boxes. Okay, so this is just evaluating the intersection over union, and we're given two bonding boxes, A and B, and with this image coordinates, and this is the bonding. We can take this as ground truth or this is predicted, and find the intersection of union. Let's try to do this. 2, 4, 8, 10, 5, 6, 12, 14. So typically image coordinates is something like this. 2, 4, 8, 10, 5, 6, 12, 14. 5, 6, 12, 14. So this is 2. Let's say this is 4. This is the top left corner. And another one is at 8. See, something like this. 8 and 10. Okay, 8 and 10. So this is the box. And another one is 5, 6, 12, 14. Starts at 5. Something here. 6. here, I guess. Um, yeah, somewhere here, I guess. Is 8, 26, and probably 12, 14. Let's take this history. Okay, something like this. Okay, so uh, all we need to find here is this area, the intersection,
about the entire area.
and the overall area. So typically, one way to do is we just find this area, find this area, and yeah, you add this. So they call this as A1. I call this as A2, right, and just do
That
A1 plus
shaded
A.
region will be added twice,
Yeah,
right?
so we need to remove it once, right? A1 intersection A2. The shaded region, we need to remove it once. So this will
Okay.
be A1 unit. Right, so A1 intersection A2 divided by A1 union A2. Okay, so what is this coordinate? We need to find the differences, right? To find the area, we need to find this length. And this coordinate is what? 5, right? This is 5. And what is this thing? 6 here, right? 5 comma 6. This will be 6. So this is the difference. 4. 10 minus 6 is 4. And this is 8 minus 5 is 3. And this is the intersection part. 4 times 3, 12. And similarly, we can find the boxes areas and just, I think it's solved in the slide. We can go over. Okay. So this is the dual, right? The intersection area. And the first area is this 36 area, and one is the union is this, intersection is this, and just 12 over 80 is the answer. Okay. Yeah, let's go to the second question. Not second, probably fourth question. Now, when we do the object detection, what happens is this typically objects in the image are less compared to your background class. Right? So typically we classify the background with a class called background. So and it will be pretty easy to classify background and ignore the true classes because of the natural class imbalance that is introduced. Right. So the focal loss is something that is introduced to address this issue. Right? It's just a small modification to the cross entropy loss. And so, which of the following statements are true? Right? A focal loss applies a scaling factor to the standard cross entropy loss, which is true here, 1 minus p per gamma, to reduce the relative loss for well classified example and focus more on hard misclassified examples. So that's true. And Now, increasing the value of gamma in focal loss will reduce the contribution from the hard examples, thus making the model focus more on easy examples. That is, you're saying
Why is A true? I didn't get it.
A is true because so focal loss uh, it creates this thing. What should I say? Uh, if you're confident correctly, say with a probability zero point 0.5 by applying focal loss, and it is giving you say loss some zero point 0.1 or 0.3. By applying the focal loss, we end up if it is classifying correctly, the focal loss will make that loss to be much lower than it is, right? So yeah. So by applying a scaling means this part we are talking about 1 minus p per gamma, right? So typical cross entropy loss is minus log p. That's it. Um, I'll draw and show you. Let's go through the options quickly. And the parameter alpha focal loss is used to address imbalance between giving more weight to minority classes. Okay, the focal loss is particularly effective in scenarios when there is significant imbalance between the number of foreground and background classes. This is true. Okay, so yeah, so this is B is false because it is saying exactly opposite to what focal loss is supposed to do. Okay, and yeah, coming to that, right? What I was saying is this: ignore alpha for now. So this is our focal loss. Okay, and let's plot this for different values of gamma, f of p. Call it as f of parameterized by gamma. No, gamma is zero. It is our usual cross entropy loss, something like this. Okay. If I increase, say this is gamma is equal to zero, right? Gamma is zero, and say call some p is 0.6 here, just for sake of reference. Right now, I increase gamma to say 2. What happens when we put gamma and we assume, let's say assume that anything above 0.6 is classifying correctly. That means they are easy to classify, easy classification. Point is once we are classifying correctly, right? I don't want my loss to show up like this because I don't want my easy examples. I don't want to learn anymore from my easy examples. So that's the whole idea. If I set gamma to 2, it will do something like this. Okay. So what is happening
So
is the contribution of loss from the easy examples have been reduced.
so gradient will not flow. Is
Exactly.
that
Even if it flows, it will flow very less.
will be very less?
Yeah. So most of the model may end up focusing on this part.
So misclassified region.
Yeah. So this is a trick when you have class imbalance or something, right? And one can use this. Okay. So yeah, now coming to the object detection part. So one should, to answer this, we should know what the difference between RCNNs and fast RCNNs and faster RCNNs. Right, so I quickly go over. Um,
Yeah, like I'm aware of their differences.
okay, you are
Please
aware.
give one of the options. Yeah.
Yeah, anything. Yes. Just for the sake of completion, you can just quickly go over. So, RCNN is where I think the first neural net based detection is being done. I mean, here they do selective search, and come up with some 2000 proposals for detecting objects on an image, and each proposal is sent independently to the CNNs,
Yes.
right? Yeah, fast RCNN still uses selective search, but with one forward pass, they're able to get the features. One forward pass.
Okay, here I have one question.
Yeah,
So in fast RCNN, we have the input image, we pass it through the convolution, and also using selective search, we get the region proposals. So
right.
those region proposals are mapped onto feature map. So here I want to ask is, so feature maps will have lower dimension, right? Because it went through
Right.
convolution, the spatial will reduce. But
Yeah.
the the region proposals that we got it from the input image, so that dimension will be much higher. So how that will be dealt with?
So typically, what they do is, let's say we have this image here, right? And say we, after doing so many layers, and we end up something like this. Let's okay. Now, any area that is mapped onto this original image will have corresponding map in the reduced feature map, something like this.
Yeah,
Okay,
true.
and it may not align exactly with the pixels here, so for that they do some interpolations, typically bilinear or some kind of interpolation they do, um, because it you may end up getting a fraction here, right? Something like this, something, okay, something like this. Now you have a feature map for this location, and this location. What if you end up getting a region something like this? If you want to end up, right, something like this, right? So you know here what is the value. Then they do some interpolation to get the value in this regions. Yeah. So they you interpolate from the adjacent information if you fall in some fraction space. Okay, so I think this is faster RCNN. They just instead of going through the selective search, they introduced RPNs, region proposal networks. Okay, so this is it. So we think we can answer this question. Which of the following statements are true regarding two-stage object fast RCNN and fast RCNN? Fast RCNN improves upon RCNN by integrating the region proposal step into network, eliminating the need for algorithm for getting the desired regions. Faster RCNN further improves fast RCNN by introducing region proposal networks that share conversion features with the detection network,
B is
making
true.
object B is true. C, in faster RCNN, RPN generates object proposals directly from the raw input image without using any convolutional features. This is wrong.
This is false. Yeah.
Yeah. Both fast RCN and RCNN use a sliding window approach to generate region proposals, but faster RCNN RPN generates higher quality proposals, reducing no. Faster RCNN uses selective search for getting
Okay.
the region proposals. Faster
A-
RCNN
a-
uses RPN. Yeah.
Sliding window means like I think it uses like there is a shared convolution network, right? In CNN.
Right.
So is
Right.
that so that is sliding window?
Right. So whatever
Okay.
we do, right? So any box that specifies the region of interest, right? And we want to get the feature map corresponding to that box. So typically, what we do is we just do a sliding window, right? Initially, um, and yeah, this is a unit segmentation based question. Which of the following statements are accurately describes the key characteristics and functionality of unit model? Unit model is characterized by its use of fully connected layer at the end of the network, which ensures the entire image is classified as no. It's not true.
False.
Unit model uses an encoder decoder structure. This is true, where the encoder downsamples the input image to capture context and the decoder upsamples it to
B is true.
use. Yeah, this is true. And unit relies only on conv layers without any pooling operation. It is
Yeah,
no.
true.
Is it true? No, right?
Yeah, I think
We
without
do pooling operations, right?
oh, we have pooling operations.
Yeah.
Okay.
In unit architecture, skip connections are used. I don't know. I don't think so. Skip connections are used.
I think skip
Um,
connections are used from encoder to decoder, right?
I don't think so because it may just
Uh,
end up mapping learning through that shortcut.
yeah, but in the architecture, if I see unit from encoder information flows, right? Unit architecture.
Yeah, but the entire information is supposed to flow through the bottleneck, right? Otherwise,
Uh, can you open the like image of unit? Then I think I can like I don't know. I'm like confusing. I'm getting confused with what I don't know.
you
Yeah, these middle arrows I'm talking about. These are skip connections, right?
I don't think so. They are skip connections. I'll get back to you on this because
Okay.
intent is not to learn through this mappings. It should go through this. Anyways, I'll get back to you on this.
Okay.
Okay. Um. Yeah. Think that's all. We can go to your this question last week.
Yeah.
Okay. So
Okay. Before that, I wanted to ask you something. So
yeah.
actually, I was thinking of pursuing part-time PhD on AI. So do you think professors accept part-time PhD students?
Maybe we can take this discussion offline because right now we are recording.
Okay. Okay. Sure. Sure.
Okay, once I stop recording, we can take this discussion offline.
Okay. Sure. Sure.
So the question was on L2, right?
Mm.
So I have seen that part. So typically, I think they assumes loss, something like this. W minus W star times H. And this W star is supposed to be an optimal solution
Yeah.
of the problem at hand. And say
Exactly.
the
Not this formula.
yeah, can you write down what is the formula? Can you tell me? I'll write down,
Yes.
or
Yeah.
you can
Sure.
share.
Okay. Okay, sure, right. So that actually involves, eigen decomposing this H matrix, Hessian matrix. After that, the formula that you get.
Yeah, I was planning to derive that actually.
Oh, actually, if you can, the derivation I got it, but I'm thinking like the equation why it works. Like why if I change the basis vector, then scale it, using the eigenvalues, then I can go back to my original basis vector. It works.
Can you tell me what is the formula if you have already have it?
Yeah, yeah, sure,
I'll
sure.
check that. Yeah.
So it is your Q,
Q.
then within brackets, you write, I don't know what this symbol is called. Let's say if it is lambda, lambda plus alpha I,
Okay.
then you close the bracket and put an inverse sign,
Okay.
and then again lambda,
Okay.
and then Q transpose, then multiplied by W star.
W star.
Yeah, yeah. Your this lambda is not, I think, that first equation you wrote, not that one. I think, yeah,
It's the same, right? This and these are same, right?
yeah, same, yes, same.
Yeah. So this lambda is, I think, diagonal matrix with
Yes,
eigenvalue
eigenvalues.
Hessian, right? Of H. So basically, what is happening here is, if I can call this as W tilde something, W tilde or something like, right. Um, Now what the impact to W tilde that is happening is lambda I by, lambda I plus alpha. Okay. So on the ith component of this W tilde. Now, what is this? What is this telling is, if my regularization is strong enough, alpha is bigger than say lambda I, right? Then my new W is decreasing the weight, uh, right? Um, So if I mean it is clear why it is reducing, because if it is much more than lambda, the weights are reduced. Now how it is
Zero. Like, can I consider that it will be close to zero? This
no,
first
if
term.
it depends on alpha. If alpha is too much, say whatever, much bigger than lambda, then yes, you can ignore this term completely, and this will
No,
be
that is what I mean. Like everything close to zero, right?
yeah.
The lambda by lambda plus alpha, that will be close to zero.
Right, that's true. And weights will be zero. And you can see from the objective function itself, if my alpha is dominating so much, right, my gradient will focus only on optimizing this, not this. Right? So yeah, I'm just minimizing now 2 square. So which optimal, which solution is zero, right? This is what.
But
Yeah.
here I would like to ask is, we can't say, right, that that first summation term will be less than alpha multiplied by norm of that gradient. Sorry, a weight matrix.
Um, if my second cost function, if I make sure that um, if okay, let's say my search space is limited, right? My search space is limited to some wall, let us say. Then this function is bounded because frankly the max value of this function will be the top eigenvalue of this h, times the maximum radius on which I'm searching. Right? You can prove this. Okay. Now, what happens in that scenario is I am limiting my the max value if this is this, and if I choose my alpha much bigger than this value, it will ignore this for sure. It may have some term, but it will ignore. So my optimization only revolves around small this part. Yeah.
So what I understood by reading is that alpha times norm of this weight matrix, that is actually the radius of this circle, right?
Yeah. Radius of the
Yeah,
circle. Yeah.
and that first summation term that will have some curvature. So I am limiting my weights to stay within that circle and choose the minimum loss.
Yes, that's true. And if you are insisting more on alpha, right, you end up falling closer and closer to this thing. And if your objective function is somewhere here, let's say, right, and you will be much far away from that. And if you
Okay,
relax
one
this,
thing,
you may keep approaching that. Yeah, yeah, tell me.
uh, one quick question. So, how can I increase the radius of this, circle? Is there any way?
Yeah, yeah, yeah. If you increase alpha, your radius is reduced. If you reduce alpha, your radius is more.
Okay, okay.
Okay.
So, inversely proportional.
Yeah, yeah. Anything else?
I think, yeah, fine.
I can
I
stop
don't know. I think
recording.
sure, sure. I think if I don't see it with my eyes how it works, then you know,
Okay.
little bit of still this thing. Like I understand the overall concept, I got it, but okay, then I think I'll try to visualize it my own way.
Yeah, I mean, it's not always possible to visualize anything beyond 2D, frankly. So
Yeah.
we rely on analytical arguments most of the time.
Okay, I'm good.
Okay, then I'll stop recording. We can address your whatever is question, right?
Uh, yes, yes. So I
Uh,
was thinking of pursuing. Can I ask now? Or yes, sir.